more minutes? Everyone's ready. Okay, welcome back. Wonderful. Okay, so second talk about Quivers and cohomological Hall algebras. And of course, I will just start by reminding you of what we did yesterday. So people can still catch up. And so yesterday, we first of all introduced the concept of quivers and their representation. Quiver was always notated Q, consisting of vertices and arrows. And representations quiver representations were given by vector spaces for all the vertices of the graph and linear maps for all arrows in the graph. And we have seen some basic notions about then equivalence of quiver representations, subrepresentations, exact sequences. So, and okay, and then we transformed this into a geometric setup, geometry, and this is summarized the following. We have GD acting on RD. So RD is this universal parameter space for all representations. This we wrote as direct sum over all arrows. D was a dimension vector. This was just a space of J cross Di matrices. The group GD was a product of general linear groups along the vertices, GL Di of C. And this action was given by GF G inverse. Let me write it down again, because this action map is so important. GI acts on F alpha as GJ F alpha GI inverse for all the arrows alpha I to j. And this is the action map. I'll write it down separately in a minute. Okay, so so this was defined in such a way that tautologically the orbits are the equivalence classes of quiver representations. Yeah, so this group action solves our classification problem, translates our classification problem for quiver representations into geometry. And then I argued that, well, you better don't take the orbit space RD divided by GD. This is a topic which we will discuss later today or tomorrow anyway. But instead, I showed you that there is a very nice cohomology theory for group actions on spaces where the group action is not so nice, not free or whatever, equivariant cohomology. And this we use to define the coha, which I will now repeat. The coha of Q is defined as, I take the direct sum over all possible choices of dimension vectors, and then I take the GD equivariant cohomology of the space RD, and on this whole thing I define a product star, and I will now show you again the essential step in the product. Well, yesterday it took a full blackboard going through all the steps, and I showed you all these identifications which just come from the general theory of equivariant cohomology. Today I will just show you the essential step, the action map, and discuss it again a little bit because there were questions about that. Okay, so the essential feature is we start with a cohomology class, an equivariant cohomology class in dimension D, a cohomology class in dimension E, and then after a long chain of identifications, we can write this as a cohomology class with respect to the group G, D plus E for a space which I will define, which I will discuss again in a second. This is essentially the next to last step in the sequence of identifications yesterday. So, and then I argued that from here there is a map which I called action lower star action to the equivariant cohomology of the space R d plus E. Okay, and this is this map. This is the definition of this multiplication star. So star is essentially up to all these identifications, it's just action lower star. And this final map I will now write down in a bit more detail. Okay, so this is a picture for the action map, and that is the last bit of geometry for today, and then we'll turn everything into algebra and perform actual calculations. And I will also present to you some challenges already today, where to start with your research on cohomological Hall algebras if you want to. Okay, because I discovered yesterday in preparing this talk, I discovered that there is really one very simple coha which is not really well understood yet. I always thought, well, okay, it's so small, this is well understood, but it isn't. Okay, so there will be some challenges for you, but okay. Back to the action map. So we have this group action there. This group action there you can write as a map GD cross RD to RD. And it just takes colors. And it just takes a pair, GF and maps it to, well, G times F. Symbolically. Now I will omit all the indices, yeah? So this is just this action map. That is the original action map. All right? Now, inside, let's now turn to D plus E, because that's what I need for the Coha product. And of course, we also have the action map. Inside RD plus E, we have those representations which have upper triangular block form. And this, I've argued yesterday, means that fits in the middle of a natural exact sequence. Yeah? So here is this block is a sub-representation. This block is a quotient representation. That was the essential information. So this is a subspace in here, and we can, of course, restrict the action map to that subspace and just map from here to here. No problem at all. Furthermore, inside this group, GD plus E, you have a similar subgroup. You also have a similar subgroup where the lower left block is 0. And this works fine as a subgroup because, well, elements of GD plus E are tuples of invertible matrices. And such a matrix is invertible if and only if the diagonal blocks are invertible. Yeah? So this is an extension of the product of smaller groups, GD cross GE. Okay, so this thing acts diagonally or anti-diagonally. It acts on the right on G and on the left on here. So we can form the quotient by this group, by this subgroup, GD plus E, cross this subgroup. And let me write down this group action. This you have to see. It should be in green because that group action was in green too. So if I have an element in here, H, it acts on a pair GF as G inverse, GH inverse, H dot F. This is this anti-diagonal action. Yeah? It acts on the right, from the right, on GD plus E, and because it's an action from the right, you have to invert it, and on the left here. And now you see the action map, which just takes the product of these two, is invariant for this subgroup, yeah? Because if you just take the product of GH inverse and HF, the H is cancelled, and you get the same thing, G dot F, yeah? And that's why the action map still gets an action map on that level. And now the marvelous thing about this map is it's proper, yeah? The original map is definitely non-proper. This is proper. This has to do with the fact that this subgroup is a parabolic subgroup. Yeah? And the homogeneous space group divided by this parabolic is a proper manifold, it's a compact manifold. So this is proper. Now, one more color. This action map is proper. And now for a proper map between manifolds, you have a push-forward map in equivariant cohomology, which in first approximation you might think of integration along the fibers. Yeah? So this is a proper map. It has compact fibers, so you can integrate along the fibers and push a class down. And this is how this action map here works and why it works. Yeah, that was this missing bit of information, this diagram, which some of you asked me about after my lecture tomorrow. So I thought I would give you this diagram in all details so that you see why are we first factoring this action map through this space. Important thing is that this is proper, and then you have a nice map in cohomology. All right, so this was both a reminder of what we did yesterday and somehow finishing the argument for the definition of the Coha. And now, well, fact is that the Coha is a nice associative algebra. This I will now write down. And then we will turn everything into algebra. So, fact, Coha of Q is a n to the Q0 graded. And there will be a small exclamation mark here, which I have to explain. NQ0 graded associative and unital Q algebra. We haven't seen Q, the rationals, anywhere in the notation. I just mentioned briefly that this is the coefficient field for all our singular cohomology. It's all with rational coefficients to avoid potential torsion phenomena. Well, now this is a bit debatable. I have to tell you why. Well, I mean, the multiplication is definitely n to the Q0 graded. You start in degree D, E, and you end up in degree D plus E. Yeah? But yesterday I showed you that there is another grading on the cohomological whole algebra, namely the grading by cohomology degree. Now the problem is, this whole chain of identifications is not compatible with cohomology degree. If you start in degree A here and B here, you do not end up in degree A plus B, but the degree is twisted, is shifted by a non-symmetric bilinear form, which plays an essential role, which we will discuss later today. It is somehow twisted by the so-called Euler form of the quiver. And this we have to see. So at the moment, it is not graded with respect to cohomology degree, which we will remedy later, but it's just NQ0 graded. But, well, okay. So, yeah. That ends part 3 of my series, and this is now part 4. Shuffle description. Cohas are expressed algebraically, they are shuffle algebras with kernel. That is mysterious, and this I will explain. So Cohas are shuffle algebras with kernel. And to start, let me motivate this as follows. Okay, we start with an observation. So the Coha is built out of these equivariant cohomologies of these spaces Rd, which are still on the blackboard, which is great. So let's make an observation, or let me help you in making an observation. Yesterday I showed you several properties of equivariant cohomology. Yeah? So equivariant cohomology is cohomology of the quotient in case the quotient is nice. So if you have a free action, which we definitely don't have. Equivariant cohomology splits into cohomology of the group and cohomology of the space in case we have a trivial action. No, this action is not trivial at all. Then we had another fact that equivariant cohomology stays isomorphic under contractions, equivariant contractions. And now, look at this action here. This action is definitely linear in the space Rd. If you just add f and f prime here, this is compatible with this group action, which is just conjugation. Yeah? So this is a linear action. This action is linear. And Rd is just an affine space, so you can contract it to the origin. And this contraction to the origin is compatible with this linear action. And so this gives us the absolutely shocking insight that this is isomorphic to the equivariant cohomology of a point, because we can contract Rd equivariantly to a point. So it's contracted to a point, so all this looks completely pointless. I mean, why did we define all this complicated action when at the end we don't need it at all? Yeah, it's just gone. This whole space of quiver representations is gone. It's contracted to a point. What's going on here? Well, now comes this complicated Coha product to the rescue. The equivariant cohomology itself does not depend at all on the quiver. It just somehow sees the vertices. But this product, because it involves this complicated correspondence of exact sequences, this product heavily depends on the quiver itself. This is the important observation, yeah? So this looks like everything is completely trivial, but product depends on the arrow structure of the quiver in a very essential way. Okay. Oh. We almost had to stop because it looked like we did something completely trivial, but now we are safe again. We have something non-trivial, and this something non-trivial I will now describe to you. So now the question is, if I use this isomorphism, yes, please. No, in general not. Yeah, only for very special relations. Yeah. That's the problem. That's one of the problems. Yeah, we will also see this problem as soon as we will see this problem in the disguise of introducing stability on the quiver, where then instead of the whole of Rd, we just take the semi-stable locus, which explicitly rules out the origin, so there's no contraction there, and then you get something much more non-trivial, even on the cohomology level. Yeah? But yes, I mean this is one of the features of this whole thing. But okay, so this is strange, but yeah, the product depends on Q1, but now nevertheless we can now say this is something we can compute. I already mostly wrote it down for you, and then the question is, what is the product? How does this product translate under this isomorphism? And this is what I will explain to you now. So the theorem is this equivariant cohomology is isomorphic via this isomorphism to the following ring. Oh. You have a polynomial ring with generators I and K, where I runs through Q0 and K runs from 1 to di. So for every vertex I of your quiver, you have di variables, xi1 to xi di. But we're not taking all of these, but we're taking this with respect to the action of the group product over all S di. Product over all I. I will write down in words what this means. We have seen one case of this yesterday. Let me remind you. In this very, very short summary of of equivariant cohomology. I've shown you the equivariant cohomology of GLN with respect to a point, that this is isomorphic to Qx1 to xn, but then you take only those polynomials which are symmetric in all the variables. And we are doing something similar here. We are taking several sets of variables, and we are looking at those polynomials which are symmetric with respect to each of the set of variables. Polynomials which are symmetric in each set of variables. So that's not yet the theorem. That's more or less just this observation. The theorem is now that I can describe the product, the star product, in this language of polynomials symmetric. Yeah? This is isomorphic to this polynomial. And in this realization, the product, the multiplication star is given as follows. And for this I need a separate blackboard. Okay. Oh, why not this one? Yeah, and now comes the formula, which we have to digest. I will just write it down first, and then we have to understand it step by step, work out some examples, and then we will slowly realize that this explicit description of the multiplication map is really our entrance gate to explicit calculations in cohomological Hall algebras and explicitly understanding them. So the product is given as follows. You have an f and a g. F is a polynomial in all these variables, as usual, this is for a dimension vector d, and this is for a dimension vector e. Yeah, so this is a polynomial. Oh, I better write it down there. So I'll continue with this formula, but I somehow give you the details of it here. So this will be the main formula, and this will just be comment. So f is a polynomial in variables xi1 to xi di, but then all I in the quiver. And g will be a polynomial in variables xi1 to xiei for all I in Q0. And in each set of variables, the polynomial is symmetric. Yeah? And now we will compute f star g, and it will be a polynomial. F star g will be a polynomial in many more variables, namely in variables xi1 to xi di plus ei in all vertices. Yeah? And these long series of doubly indexed variables I don't want to have in this formula. This formula should be clean, and that's why I just write it down as a comment. And now here, to compute this, you are taking the sum over all dE shuffles. And I have to tell you what dE shuffles are. So I dot prime, I dot double prime dE shuffles. It's a standard object in algebraic combinatorics, but we can understand it very easily. F of xi prime, g of xi double prime, that's the so-called shuffle product. And now we have a kernel, like an integration kernel for the shuffle. And this is the product over all pairs of vertices, product over all k in I prime, L in I, J double prime. And now, unfortunately, the blackboard is over. There's one more term which I have to add here. Sorry for that. xjl minus xik to the power rij minus delta ij. And this means that after the product, you continue with this. Okay. Sorry? Rij. I will define it. Yeah. So I will define the shuffles and all this notation here on the left. Okay, we can already say, well, this is maybe quite polarizing. Yeah. You might say, okay, before everything was very nice, just a very clean product in equivariant cohomology. I liked it. This is a terrible formula. I don't like it at all. Well, but this is something you can really do calculations with. This is what I would like to convince you of. So, but we need more details on what all these notions are. So first I have to tell you about shuffles. And this is really like, imagine you have a deck of cards, or two deck of cards, and you want to shuffle them together. So you have your two deck of cards, and you put them close to each other, and then you shuffle them, mix them together in some way. Yeah? And as people in combinatorics like to do things with finite set and then count how many times they can do that. Yeah? And this is why shuffles are interesting. So how many different ways are there to shuffle two deck of cards together to one deck? Yeah? Because you could have, well, we will see examples of that. And so a shuffle means we imagine a deck of cards of DI cards, a deck of EI cards, and we shuffle them together to a deck of DI plus EI cards. And there are several, lots and lots of ways to do this. Yeah? And we can formalize this as follows. So we take the set 1, 2, DI plus EI, and we write this set as a disjoint union of two subsets. This is the first deck of cards, and this is the other deck of cards. And they're somehow shuffled into each other. This is a disjoint union. And we make such a choice of disjoint union for all I in Q0. And this is this notation of DE shuffles. This is called a DE shuffle. All right. So I explained this notation. Next notation is f of xi prime. This is just a shorthand notation to avoid further indices. Yeah? We're already dealing with double indices. I don't want to deal with triple indices. This just means enumerate all the indices in this I prime set, enumerate it in any order, take these variables and plug them into f. And the order doesn't matter because it is symmetric in each set of variables. Yeah? Yeah. And that is in particular, this is why I can just say x index I prime, x index the whole set, and I don't have to specify the order of the variables because this f is symmetric in any set of variables anyway. Huh? Okay, everything fits together nicely. Wonderful. Same for G, no problem. And then there is this so-called shuffle kernel. It's a product over all pairs of vertices. And then you take the product over all cards in the first deck, all cards in the second deck. And then for this, you use the term xjl minus xik to some power. And I have to tell you what this power is. So rij is nothing else than the number of arrows from I to j. And delta ij is just the Kronecker delta. Okay. So if you see this for the first time, you don't want to do calculations with this description, but qualitatively, it's clear that this is a great thing because this is just a funny operation on polynomials. Yeah? And this is something you can really do. Whereas the original core was equivariant cohomology classes, and it's not really clear how to do actual calculations there, unless you're really, really good at equivariant cohomology. Yeah? So, but now we are in algebra. Okay, so, and as a warm up, we will now do Quivers with a single vertex. Exactly. The problem is, of course, if you, well, if I equals j, and you have no loops from I to j, then you have a negative power here. So the question is, why can you divide this whole thing by this product of differences? Yeah, and this we'll see in the example. Yeah, I mean, there's a general argument, but for the general argument, I have to deal with all these multiple indices. So let me just show you it for a single vertex quiver, and then the argument is absolutely clear. Yeah, yeah. So everything is quite material. This theorem is not so difficult to prove. It requires one important theorem about equivariant cohomology, the equivariant localization theorem. And essentially what you have to do is you have to compute a certain, one particular cohomology class, so-called equivariant Euler class. And this you can compute. And this then leads to this description. Yeah? So it's not too hard, this theorem. This was in the paper by Kontsevich and Seubermann from 2010, which I mentioned. All right. So let's get used to this. And so this is now part 5 of the talk, examples. And in these examples, we will basically deal with the Coha for the quiver, which is just a single vertex, the quiver, which is a single loop, and the quiver, which is a single arrow. And not so accidentally, these are the 3 cases which we have dealt with yesterday. And these are precisely 3 cases where we know from linear algebra the classification of representations. Yeah? And the fact that we have this classification is somehow reflected in the fact that we get a nice, or rather nice description of the cohomological Hall algebras. Okay, so this will be part 5. Wonderful. Okay, so now let's first, I mean, these first 2 cases I can subsume in one class, Quivers with one vertex and a number of loops. So let me show you what we already know about the Coha of Quivers, which are a single vertex and then a bunch of, say, m loops. We will only deal with m equals 0 and m equals 1, but with respect to this description, we can deal with it anyway. So this is now direct sum over all d greater or equals 0. And now this d is not underlined because it's no longer a dimension vector. It's just a single dimension, namely the dimension of the vector space at this vertex. Yeah, easy enough. And in each d, you have now polynomials in d variables which are symmetric. Aha, so the double indices are gone. So this is definitely a nice example. Okay, and the product is given, this shuffle product is given by f star g is sum over all shuffles. And now a shuffle is just that we decompose the set 1 to d plus e. I'm basically writing down this formula again, but in this simplified case. I'm just writing this as a disjoint union. I plug in the xi prime variables in f. I plug in the xi double prime variables g, and as the kernel, I just have the product over all k in I prime, L in I double prime, xl minus xk to the power m minus 1. Okay, so now you can copy this and see that this is really just a specialization of this formula. And luckily for us, it's now just in a single set of variables. So let me put this top. And this too. All right. Yes. Okay. And now we have to get used to this. And let's say okay. Let's start with the first example, m equals 0. This is already interesting because in this case, m equals 0, we are producing a proper denominator here. And we really want to see how this denominator will vanish. Yeah? So let's work out a particular example. Let's say we take, what kind of shuffles do I want to show you? Oh yeah, okay. Let's say just a very particular example. Let's say we take as f, we take the polynomial x1, x2, and as g, we take the polynomial x1 squared plus x2, both in two variables. Yeah? So f and g are both in the degree 2 business. This is just a completely random example because I just want to show you how to shuffle. Okay, let's write down all the possible shuffles. So we have a deck of 4 cards, which is 2 decks of 2 cards shuffled together. Yes, please. No. Sorry, yes, yeah, you're right. Thanks. It should. Yeah. So these are 2 symmetric polynomials. Thank you. Okay, so this is the 4 cards, and it's merging 2 sets of 2 cards each. And this you can do as follows. You can shuffle 1, 2, and 3, 4. You can shuffle, this is the first thing. You can shuffle 1, 3 into 2, 4. You can shuffle 1, 4 into 2, 3. And you can shuffle 2, 3 in 1, 4. 2, 4 and 1, 3. Ultimately 3, 4 and 1, 2. Yeah. So the first line is always the I prime and then the I double prime. These are 6 shuffles. 6 is the binomial coefficient 4 choose 2, and that's the general formula. Yeah. So the number of shuffles always relates to binomial coefficients. If you think about it. Okay. So then the first term is that we just take f in the first in the I prime variables and g in the I double prime variables. So that means we take x1, x2, x3 squared plus x4 squared. Yeah, and then we have to divide this by the shuffle kernel, which is you take the product over the variables in the second set minus the variables in the first set. So it's the x3 minus x1, x3 minus x2, x4 minus x1, x4 minus x2. Okay, so that's just the first term. And now you can figure out all 6 terms. Yeah, so the next, just write down the second term and then not continue. The second term is the first proper shuffle, and there you take x1, x3. You take the f in the first set of variables, x1, x3. And you take the g in the second set of variables, x2 squared plus x4 squared. And you divide by almost the same thing, but now it's x2 minus x1, x2 minus x3, x4 minus x1, x4 minus x3. So, and then plus several other variables. And you see, a priori, there's no reason why denominators should cancel. But if you work this out, if you do this calculation, bring everything to a joint denominator, then you will see magic cancellations. Yeah? Okay, so we will see the clear reason for that in a minute. So this was just an example, which is kind of pointless It was just about explaining to you this notion of shuffle. We will never see such a complicated shuffle again, yeah, in the examples which we'll do now. So this was the first example, and yeah, from this point of view, it's not clear why anything should cancel. But let us do a more conceptual calculation. Here we go. Let's shuffle x1 to the k and x1 to the L. So f and g are both living in degree 1. They just have one variable. Huh? And this is now easy to do because if you have just one variable in each set, there are just two shuffles. Yeah? I mean, at the end, you just have 1, 2, and you divide them into 1, 2, and 2, 1. These are just the two shuffles compared to these 6. And then what you get is x1k, x2l, divided by x2 minus x1, plus x2k, x1l, divided by x1 minus x2. Aha. So let's bring it to a joint denominator. This is easy in this case. The joint denominator expression is x1k, x2l minus x1l, x2k divided by x2 minus x1. And now there are two ways to argue that this actually is a polynomial. Well, first of all, you can just perform the division, just dividing the polynomials, and then you see that after difference between k minus l steps, the division of polynomials will terminate. Or you can argue as follows. When is a polynomial divisible by x2 minus x1? Well, if it vanishes whenever you identify x2 and x1. Yeah? So x2 equals x1 are the common zeros of the polynomial. Yeah, and indeed, if you plug in x1 equals x2 in the numerator, you get 0. So this thing is divisible by this. That is the general argument for this expression to yield a polynomial. Yeah? So whenever you have an identification of these variables, due to all these shuffles and the implicit signs which you have in there, everything will magically cancel because everything in the denominator is a common zero of the numerator. Yeah? So okay, so this is a polynomial. Yeah? This is a polynomial in x1, x2. All right. Mm-hmm. Yeah, and now you can perform more such examples. But at some point you realize the polynomials are getting more and more complicated. But then we have algebraic combinatorics to the rescue. The class of polynomials which you get from these multiplications is known in the combinatorics literature. Namely, it's the Schur polynomials appearing. And I don't want to get into all the story of Schur polynomials, but just somehow give you a solution to this implicit homework from yesterday. I told you that for today and for performing calculations, you better look up some properties of symmetric polynomials. Yeah? Okay. Now I will show you the properties of symmetric polynomials you need. So what do we need to know about symmetric polynomials? The ultimate source for this is the book of MacDonald, Symmetric Functions and Whole Polynomials and Symmetric Functions, which contains everything about symmetric polynomials, just everything. But for our purposes, just take the Wikipedia article on symmetric polynomials. That's definitely enough. So first of all, this ring of symmetric polynomials is a polynomial ring itself. Namely, it's a polynomial ring in so-called elementary symmetric functions. Yeah? The polynomial ring is itself, the invariant polynomials is the same, is itself a polynomial ring in other so-called elementary symmetric function polynomials, which we don't need, but it's just fun fact, this is the fundamental theorem on symmetric polynomials. Yeah? Whenever you have a polynomial which is symmetric in the variables, you can express it as a polynomial in other polynomials, in certain standard polynomials. E1 is just the sum x1 to xd, and ed is just the product, x1 times xd. And the other coefficients are intertwining between these. All right, this is the first fact. And the second fact is this has bases indexed by partitions. And partitions is just a sequence of non-negative integers, of a descending sequence of non-negative integers of length d. And there are several such bases. We just need 2 of them. There are like 10 of them, which are extremely important. We just need 2 of them. The shuffle formula I need, so I can erase this example. The first basis is the so-called monomial symmetric functions, and the second basis is Schur functions. Okay, let me write these bases down. So monomial symmetric polynomials m lambda, where lambda is just short for such a partition, lambda 1 to lambda d. This is nothing else than you take the monomial x1 to d to lambda 1 times xd to lambda d. This is non-symmetric, but now you are trying to make it symmetric with as few additions as possible. Yeah? Like in this example which we had here, if you have x1 squared, then you have to add x2 squared, and then you are symmetric, and you don't do anything else. So we plus all distinct permutations. So these are the first symmetric polynomials you might think of. Yeah? You just take a monomial and you symmetrize it as minimally as possible. Okay, and then you get the monomial symmetric polynomials, and they form a basis, a linear basis of this as an infinite dimensional vector space. Yeah? And on the opposite end of the scale is something quite fancy and elaborate, the Schur polynomials. And it's not the first symmetric polynomial you might think of, but they are extremely important in representation theory. So Isai-Schur used them, for example, if you want to work out the representation theory of symmetric groups and work out the characters of the symmetric groups, you automatically end up with these Schur polynomials very naturally. And these Schur polynomials, they come from the fact that there are certain identities between determinants. So, let me just write it down. So the Schur polynomial S lambda is a fraction of 2 things. It's the determinant of the matrix, which has entries xk to the lambda k plus n minus l, if the matrix is indexed by k and l. And then you divide by the Vandermonde determinant, then you divide by the product over all I less than j, xj minus xi. That's the classical definition of the Schur polynomial, and we will see it popping up in the context of the Coha in a few minutes. Okay, so, So the beautiful thing about the Schur polynomials is that in defining this as a polynomial, you have such a divisibility question, which we have addressed also here in this Cohom product. So let's first of all, why is this determinant divisible by the Vandermonde determinant? We can use the same argument as before. Whenever two variables coincide, xi equals xj, then in this matrix, you have two rows which are the same. And a matrix which has two rows the same has determinant 0. That's the divisibility argument. So again, just linear algebra solves it all for us. Yeah? That's the divisibility argument. So this determinant is divisible by all difference between the variables. So this is an actual polynomial. So that's all we need to know about the symmetric polynomials. Wonderful. Okay, so let me switch to blackboards. And now let's see. Sorry. Let's see what is the structure of the coha of the trivial quiver, which has m equals 0. And this we will now work out. So this will now, well, we are still in the example section, but let me write this as a theorem anyway. A theorem. It's the variable xk to the power lambda k plus n minus l. Sorry? Oh, n is d. Sorry. Thanks. Thanks for this question. That's d. That's the number of variables we have. Yeah. Yeah, see, I just copied it from the Wikipedia page, and there were n variables there. All right. Okay, so theorem. The coha of the trivial quiver is isomorphic to an exterior algebra, in a vector space with infinitely many generators. Psi 1, psi 2, psi 3, and so on. Yeah, so, I mean, these are the generators, and the defining relations are all anti-commutators are 0. In particular, all squares of these are 0. Okay, so that's what we want to prove. So first of all, we have, I have to tell you what these generators are. And these generators, phi I, are precisely, well, we take the monomials in one variable, and it's just the power x minus 1, I minus 1. So these generators are really, i.e., coha star is generated in degree 1. In degree 1, we have a polynomial ring in one variable, and we don't need to symmetrize. Yeah? And a basis for this space is given by 1, x1, x2, x1 squared, and so on. And these variables I just identify with this. Okay. Now, first of all, we can see that, so that's what I define. Then the first step you have to see is that f star f is always 0. And this you have to see from the Coha multiplication, which is still here. And it's basically the same divisibility argument which we have seen. If you plug in f and g, the same polynomial, then, well, for any shuffle I prime, I double prime, you have the opposite shuffle, I double prime, I prime. And for this opposite shuffle, you have this expression with a different sign. And so everything cancels. Yeah? So this is an easy calculation. Just stare at this formula for long enough. Okay. So, and now this identity you can polarize. You apply it to the element f plus g, and then you see the anti-commutation relation that all the anti-commutators are 0, identically 0. Aha, So we are definitely in the world of an exterior algebra. And now we just have to see that the whole Coha is generated by these guys. Yeah? And aims to show that Coha is generated by degree 1. And now this we will do with the Schur polynomials. And this is just one calculation. And you just need to know what the determinant is, how to compute determinants with the Leibniz formula. Okay, and for this, let me do the following calculation. Oh yeah, okay. Yes. Let me take psi index lambda 1. So sorry, I have a shift in the indices compared to my notes. So I have to translate this a little bit. Ah, yeah. Plus 1d, psi lambda 2 plus d minus 1 times psi lambda d plus 1. So again, we take a partition, lambda 1 to lambda d, and we are shifting the parts in the partition. We are shifting the first part by d, second by d minus 1, and last one by 1. We are calculating this multiple product in the Coha. So this is, using the definition of the psi's, nothing else than we are taking the product of x1 to lambda 1 plus d minus 1, x2 to lambda 2 plus d minus 2 times x d. Yeah. So these are all polynomials. Sorry, it's always x1. Sorry for that. It's always x1. We want to prove that the Coha is generated in degree 1. So it's always just x1. Okay, always x1. So now we're calculating this product. So it's now, every single star is a shuffle product. And now here we are taking an iterated shuffle product. Now imagine what we are doing. Altogether, we now have d variables in this product, yeah? And we have d variables, and they are shuffled. So we have d cards, and we have d decks of 1 card each. And we are shuffling together d decks of 1 card each. What are we doing then? How to shuffle together d decks of 1 card each? We're just taking the cards in an arbitrary ordering. So we are summing over all permutations of d. Yeah? So this iterated shuffle product is the sum over all permutations in SD. And then we take this permuted thing, which is like, where did I do this calculation? Ah, yeah, that's very good. X1 to the lambda sigma 1 plus d minus 1 times xd to the lambda sigma of d, and then I'm always dividing by the shuffle kernel product over all I less than j, x sigma j minus x sigma I. Okay, so this will be over in 2 more lines, yeah? So sorry, this is I just really want to have one Coha computed in all details and really give you a complete proof for that. So this is why I'm insisting on giving the details here. So this is how it looks like if you write down this default shuffle product. Yeah. But now we do the sign trick, because this product here in the denominator, it's always the same product. It's the product over all difference of distinct variables, but always in a different order. So we pull this out in always the same order, 1 less than j, xj minus x1, and this will just introduce a sign in this sum. This will then be a sum over permutations, minus 1, 2, well, guess what? It's the signature of the permutation, and then you have this x1 to the lambda sigma 1 plus d minus 1 times xt lambda sigma of d. So that's our usual sign trick, which we have already seen in the examples before. And now this you recognize by Leibniz formula as a determinant. This is precisely the determinant of the matrix, which has rows, which has xk and then lambda k plus d minus l as the kl entry. So this whole thing is the Schur polynomial as lambda. Okay. Whoa. Yeah. Okay. That's lots of indices and lots of permutations which you have to handle. But at the end, you see, we get all Schur polynomials as iterated products of these psi's. Now, the Schur polynomials are a linear basis of our symmetric polynomial rings. Yeah? So we get a linear basis as images of the product, so these are generators. And they are a basis. And they form a basis of Coha dot. So the whole thing is generated by the psi's, and they anti-commute, and then you easily see that this is indeed an isomorphism when the Coha is computed. Okay, so end of the proof. Aha. So the rest of this lecture will be definitely more relaxed. But I think it's important to see that one can really completely describe the Coha just by standard algebraic tools, standard algebraic tools to symmetric polynomials. Okay, so, all right. And now I think, now we will deal with a single vertex and a loop. I will not show you the details, but they are quite similar. You can argue similarly, but I will just show you the final result. And now you have all the tools which you need for proving this. No, I better erase this. So, yes, please. Yeah. No, unfortunately not. I mean, people did experiments with, I think the most general theory you can do is equivariant cobordism. And then you have the Lazar ring as a coefficient ring, but there's not much more information. So you don't get any fancy Hall-Littlewood or McDonald polynomials, unfortunately not. You get a bit more interesting things if you pass to K theory, equivariant K theory. But yeah. No, I mean, the only thing you need is that in equivariant cohomology, you have an equivariant localization theorem, yeah, to get the shuffle description. Yeah, that's all. I mean, it would be wonderful to have to somehow boost the cohomology theory so that you get, instead of Schur polynomials, you get Hall-Littlewood polynomials, yeah, or even McDonald polynomials. It would be wonderful, but I don't think anyone has figured out a way to do this. Yeah. Okay, I will now modify this theorem for one loop. And the great thing is that we can almost copy the proof But I want to write it down again because it's unfair just to erase the parts and replace it by the correct thing. So second theorem is, what is the coa of the one-loop quiver? That is not an alternating algebra, but a symmetric algebra. It's the symmetric algebra in generators phi 0, phi 1, phi 2, and so on. So if you see this, that for 0 loops you get an exterior algebra, and for 1 loop you get a symmetric algebra, then of course you could argue that for the 0 loops you get fermions, for 1 loop you get bosons. So the question is, what do you get for 2 loops? We will see later what you get for 2 loops. Crazy things which nobody really understands. Okay, so the proof is similar. So the phi 0 is nothing else than you take x1, phi I is nothing else, you take x1 to I. So again, coa is generated in degree 1. The coa is no longer anti-commutative, but it is commutative. I cannot quickly show you the reason why, but what you see is the coa is the so-called shuffle algebra, and this strange product of differences of variables just vanishes. Just a shuffle algebra, and then we have already argued if you have one shuffle I prime, I double prime, you can just switch parts. And so this is the reason why it is commutative. And now you just have to see why is it generated in degree 1. Well, guess why I mentioned the monomial symmetric functions to you. You can see that the monomial symmetric function is nothing else than the product of phi lambda 1 times phi lambda d up to a certain scalar, which is not interesting. You know, you don't get a van der Waals determinant. Yeah? You're just summing over all permutations. Yeah? And the monomial symmetric function was you're taking the monomial and summing over all distinct permutations. Here we're just summing over all permutations, so we are somehow over-symmetrizing a little bit so you get a scalar multiple, but that's it. Yeah? You just get a multiple of this, non-zero multiple, and these are bases, so you're done, everything is again generated in degree 1. So it's quite a similar proof, even simpler, but it is only the second case. All right. So now comes the challenge for you. I will just give you no, okay. So, yeah, okay, 15 minutes left. I will give you one brief fact about the coha of the 2-loop quiver and show you a beautiful formula, which I like, because I found it. And then I will show you the coha of the single arrow quiver and give you a challenge. And then we have definitely done enough for today. Okay, so I will pick up on this coa of the 2-loop quiver tomorrow when we go to the big theorems about cohas. So today were basically the examples, and tomorrow will be the big theorems. And but I just want to show you one theorem. What about the coha of the 2-loop quiver? It's no longer generated in degree 1. It's still a symmetric algebra, or at least it's a, well, it's a supersymmetric algebra. It's a graded symmetric algebra. Graded symmetric algebra. What does this mean? There will be a set of generators which has odd degrees and even degrees. In the even degrees, it's a symmetric algebra, commutator vanishes. In the odd degree, it's an antisymmetric algebra, the anticommutator vanishes. Yeah? Graded symmetric algebra. Over a certain set of generators, V primitive, and another free variable Z, And the big formula is that nobody really knows what this V print is, but at least we know its dimension. So this is graded. So this is somehow a collection of all the generators. And you have generators in each degree, unless the case of the 0 loops and 1 loop, where you have only generators in degree 1. But now you have generators in all degrees, and the dimension of the degree D part is 1 over D squared, sum over all divisors of D, number theoretic Möbius function, assign D minus E, yeah, and a binomial coefficient to E minus 1 over E minus 1. And this grows really, really fast, yeah, because the growth behavior of these binomial coefficients is pretty fast, yeah. So you're getting more and more sets, more and more infinite sets of generators in each higher D, yeah. So you need terrible amount of generators. So this is the next step after fermions, bosons. Then you get these kind of particles, and you have this exponential growth. I mean, these are. You could argue these are really the irreducible BPS states for whatever theory is behind that. And it's already growing exponentially. So this is really, really bad. And I will pick up on this tomorrow and show you the general theory behind this. This is an example of a numerical Donaldson-Thomas invariant, or numerical BPS state count. This is a numerical DT invariant. This will be the first thing we discuss in general tomorrow. Okay, that was some outlook in this direction. And now finally, the final example of a COA, which you can compute with this shuffle description. And the challenge is to find a better presentation than I will give you. So final example for today. Is the coha of a single arrow, I, J. So before writing this down, I will promise you that tomorrow will be not as computational as today. So tomorrow we'll see the big theorems and put the COA into several different contexts, in the context of stabilities, moduli spaces, Donaldson-Thomas invariants. So we'll somehow come back to the geometry. But I think there's really lots of things to discover about the cohomological Hall algebra, really just from this shuffle description. Yeah? So I mean, for example, the fact that the COA for this quiver is a graded symmetric algebra over whatever, this was done by Efimov algebraically by a Gröbner basis argument. Yeah? He just showed you sorting Gröbner basis of symmetric polynomials that the COA is a graded symmetric algebra. Yeah? So there's lots of things to do just algebraically. That's why I really wanted to show you how calculating in the COA works, but tomorrow will be more general context. Okay. No, it's definitely much more complicated varieties. Yeah. So this you will see tomorrow. One can describe this set of generators geometrically as cohomology of some spaces, but definitely much more complicated than Grassmannians or flag varieties, unfortunately. Okay, so the COA of this is generated by symbols psi I and eta I for I, 1, 2, and so on. And the translation is as follows. Psi I is the xi1. Oh, sorry, that's a double I. K, sorry. Psi k is the xi1 to the k minus 1, and eta k is the xj1 k minus 1. Haha. So this is the first quiver with two vertices. So unfortunately now we have two sets of variables. Yeah, we have one set of variables at the vertex I and another set of variables at the vertex j. So we have two cases where we only have one variable. We have only one I variable and only one j variable. And this gives us two infinite set of generators, and here are the defining equations. So first of all the psi's anti-commute and all the eta anti-commute. Psi, psi anti-commutes, and the etas anti-commute. Well, because if you just deal with the psi's, then you can forget about this other vertex. Then you're dealing with the trivial quiver, and this we have already seen. That just gives an exterior algebra. Now we need mixed relations between these two, and these were worked out also by Quivers and Stoiberman. And the mixed relation is that psi k eta L is, I have to shift the indices, eta L plus 1 psi k minus eta L psi k plus 1 for all k and L. So these are defining equations for the Coa. And I'm not convinced that this is the best description. So there should be better descriptions than this. I mean, this is some of the most natural set of generators you find, and then you get this set of equation defining relations, which is not nice. This is a really strange kind of relation, and there should be better ways. And I think there's really, there are structural approaches to finding better descriptions, but I think just doing an ad hoc approach would also be helpful. There might be a description which nobody yet thought about, which might be much better than this. So if you're interested in getting your hands on the Coa, find a better description just for this Coa. I think there's something going on there. Okay, so this ends all the calculations for today. Thank you very much. Well, one can introduce a third set of generators in terms of there should be a third set of generators where you have only one I variable and one j variable. And introducing this third set of generators should then just simplify the relations. Yeah? So this is already implicit in this Quivers-Stoiberman paper, but this is still not optimal. So I have an idea of what to do there. Yeah? So maybe, this is the minimal set of generators, but the relations are maximally complicated. Why not introduce more generators so that at least the relations are simplified? Yeah? So there might be a way, but there might be different ways. It's not unique. Sure. Yeah. Yeah. Equivariant K theory, just for a point with respect to the group G, is the representation ring of the group. So it's the same polynomial ring, but now the variables become invertible. Yes. Yeah. So it's not symmetric polynomials, but symmetric Laurent polynomials in variables x1 to xt. Yeah. But yeah, there are some papers about this K-theoretic Coha, but I don't really know what's going on. Yeah. Thank you very much.